Okay, welcome back. Let's continue with our lesson. And in our last lesson, we were looking at examples of where the arithmetic circuits are applied in zero-knowledge proofs and real-life situation. So today we continue with those examples. The example we're looking at today is how do you verify a sorted list using arithmetic circuits? So that is what we'll be looking at in today's lesson. So I've noted here that in zero-knowledge proofs, we really need to verify certain properties of data without revealing what the data is. And so one property is that of the sorted list. So that's what we'll be looking at. We want to, for instance, we'll be looking at the application of this. We'll be looking at the range, for instance, if the given information is within a given range, without necessarily having to reveal what the information that the verifier claims to know, the exact information, what the exact information is. So we just want to say that the verifier has given us information within the given range, so that is not giving us something outside that range. So the knowledge of sorted list, identifying if a list is sorted, that is, if a list has been arranged in ascending order, is not only practically relevant, but is used in very many applications like privacy-preserving applications. We'll also see that it's used in areas like expressing constraints in arithmetic circuit form. So this is the other way we can also use it. Other than using it in privacy-preserving order verification, you can also apply it in this area. Now, so these are the things you need to know. Our target is that by the end of this lesson, you should be able to know the following. One, you should be able to know what it means when we talk of a sorted list. What does it mean? What is a sorted list? What is a sorted list, in other words? What is it? And how can we express this condition mathematically? How can we express sorted lists mathematically? So that is one thing that we are supposed to know by the end of this class. And the other thing is we're supposed to know how to construct arithmetic circuit for sorted lists. And then you're supposed to analyze efficiency. That is understanding the number of constraints required and how they scale with the size of the list. Then finally, the other thing you need to know by the end of this lesson is must know how to discuss applications. That is where sorted lists, the knowledge of sorted lists verification is used in ZK proofs. Of course, I've given some of the ways, some of the areas where it will be applied, like range proofs and private order preserving computations. But the thing is, we should be able to discuss that by the end of this lesson, how it's used in these areas, the knowledge of sorted lists. Now, so I'll begin by an example. And of course, before that example, of the definition. The example is you've been given a list and you need to sort it. No, you need to verify that the list is sorted. You need to verify that the list you've been given is sorted. So that is what the example is about. But what do we mean by a list being sorted? So a list, this is the list I'm referring to. We would say that this list is sorted if it fulfills this condition. that the elements of this list are arranged in ascending order. We cannot have this element A1 being larger than A2. That can never happen. So if it's that, then we are saying that it's not sorted. So if the elements are mixed up, they're mixed up so that they're not arranged in some order, then we are saying that they are not sorted. Yes, but just as we had mentioned, a list that is sorted is a list that is arranged, elements are arranged in ascending order, each of them. So the element on the left, on the right, is less than the one on the left or greater than it. No, it is A2 is greater than or equal to. A2 is greater than or equal to A1. A3 is greater than or equal to A2, and so on. So in that order. So if elements are arranged in this form, then we say that this set is sorted. Otherwise, it's not. If elements are just mixed up, then we say that they're not sorted. Now, so just as I mentioned earlier, when we're talking about arithmetic circuits, we had already seen that arithmetic circuit has one multiplication and then has addition only as the operators. So we have multiplication and addition. Now, we are introducing greater than or equal to, which is not part of what we know under the arithmetic circuit. So how do we then represent this greater than or equal to sign, this sign? How do we represent it in arithmetic circuit? So that is a very interesting concept. And once we understand that, and then we shall be seeing how we'll be using that in zero knowledge proof. Because after we are done with this, our goal is to ensure that we then look at the zero knowledge proofs and how do we write those equations? How do we verify? That is what this is just introducing us to zero knowledge proofs. So at this point, we are just verifying that the list is sorted. And this is part of what we'll be doing in zero knowledge proofs, just verifying that what we've been given is sorted, or what we've been given is in this range, and so on. So what is therefore our mission? Our mission is to design an arithmetic circuit that verifies that the given list is sorted. Design an arithmetic circuit. Arithmetic circuit is just talking about equations. These are just equations, a system of equations. So what I'm saying in simple words is that our aim here is to be able to come up with equations that would then be used to verify that a given list is sorted. In other words, the given list is arranged in some order. So once we come up with those equations, then we are able to do that. Now, I'd already mentioned this point. I'd already mentioned that the arithmetic circuit uses only two symbols, or yes, this addition and multiplication. Okay, and then equality. We have addition, multiplication, and equality, but we do not have greater than or equal to this symbol. So therefore, for us to do to write arithmetic circuit that verifies that a given list is sorted, we need to get a way of going around and to ensure that we can compare two quantities as one being greater than or equal to the other one using this sign. Since this sign is not part of what the arithmetic circuit does, it's not part of what it does, we must come up with a way that we can be able to compare two things, for instance, and say that this is greater than or equal to this. So that is what we are interested in, and that's what we'll be doing. So therefore, I want us to look at constructing a sorting verification circuit. How do we construct a sorting verification circuit? In other words, how do we come up with an equation that can show that or can verify that a given list has been sorted or is sorted? So in other words, we're looking at how do we come up with this? How do we show that A is greater than or equal to B? And yet, our arithmetic circuit do not have the sign greater than or equal to. So how do we go around this? Because that is the only problem that is facing us here. Once we solve it, and then we are done. Once we solve that problem. So I've written and said that if we had a function that it checks whether two numbers satisfy this inequality, and supposing that function is denoted by greater than or equal to AB, supposing you have this function that is denoted greater than GTE, greater than or equal to AB, then we could verify that the sorting condition is satisfied by just verifying that. Now, these are two, we are just arranging. Supposing we had AN greater than or equal to AN minus 1, which was greater than or equal to, AN minus 2, which was greater than or equal to, all the way up to greater than or equal to AN, A3, greater than or equal to A2, greater than or equal to A1, and so on. So we want to say, suppose we have a function. Suppose we have a function that can tell us that these two, which of these two is greater than or equal to the other one. That's what I've written here. Suppose we have a function that GTE, that it tells us which of these two is greater than or equal to the other. And that same function can tell us between these two, which one is greater. And that function, this same function can tell us which one between these two is greater and which one between these two, and so on. If we had such function, then we would be done, because that is what our target is. Our target is to be able to tell that this one is greater than this one is greater than this. And once we are done with that, we can come up with an arithmetic circuit that is able to tell us that, or that is able to verify that a given list is sorted. So once we have that function, then we are done. Now, but as I've already mentioned, while designing arithmetic circuits, we do not have this sign. We already said that the arithmetic circuits have the signs addition, multiplication, and the equality sign. But it does not have this. So how do we go around to ensure that we have this? We can compare two values, that AN is greater than or equal to AN minus 1. How do we go around to do this? So for us to go around to do this, we can never bring in this sign directly. What we do, therefore, we convert our values to binary. The values we have are in decimal. So once we convert them to binary, we have a way that we can now do to compare the values while they're in binary. So that is what we will then be looking at. That we can never bring in the sign greater than or equal to directly into our arithmetic circuit. But now it becomes necessary for us to convert values that we have to binary, first of all. So that's why I say here that we need to learn how to do binary encoding, because that will then be a prerequisite. You can never compare two values in arithmetic circuit unless you first of all convert them to binary. So once you convert them to binary, it becomes easier. So I've said to enable comparisons, we represent our numbers in binary. A binary number is one that is written with a subscript 2. For instance, this is a binary number, although this is a decimal number. This one is a decimal. So this binary number is equivalent to this decimal number. And this binary number is equivalent to this decimal number. So then in a short while, I'll be showing you that how you can tell that this binary is greater than this. In a short while, that's what I'll be doing it. But I just want to show you that this binary is equal to that. How do we do that? This is the least significant value. So the significant values go this way, they increase this way. These are significant values increase this way. This is the least significant value. So the least significant value is multiplied by 2 raised to 0. Then you add that to the most. Now these are only 2. So this becomes the most significant value is multiplied by 2 raised to 1. So it's 2 raised to 0, raised to 1, raised to 2. As you go to the left, the powers increase. So this is just 2. And this 2 raised to 0 is 1, times 1 is 1. So that is 3, and that's how you get 3. This is a decimal number. But the other one was binary. So you put base 2 to show that it's binary. Now, this is also binary. Let's see how we convert to decimal. Just again, you will know how to do that. This is the least significant. So the least significant multiplied by 2 raised to 0. Then plus this other one is the other one, the next significant value, 0, multiplied by 2 raised to 1. Then plus this other one is 1, multiplied by 2 raised to 2. So this is the most significant value. The most significant value. So this most significant value multiplied by 2 raised to 2 gives you 4. Then this is 0 multiplied by 2 raised to 1 will be 0. And this is 1 times 2 raised to 2. 2 raised to 0 is 1. 2 raised to 0 is 1. 1 times 1 is 1. So this gives you 5. That gives you 5. That's how you got 5. So that is how we convert a binary number to decimal. But that is not what we wanted. What we wanted was we are given a decimal number. We have to convert it to binary. That is what we wanted. So that's what I'll just show you again, how we convert a decimal number to binary, because that's what I was saying. That's what we said, that if we have two numbers and we want to compare which one is larger, we do not have that way. We do not have the symbol greater than or equal to in arithmetic circuit. We have to convert these numbers to binary. So how do we convert this one to binary? It's a decimal number. To convert to binary, we usually divide by 2, which is the base, our base. Divide by 2 and note the remainder at every stage. So for instance, 2 goes here twice, but we are interested in the remainder, which is 1. And then 2 go here once, but we are interested in the remainder, which is 0. Then 2 finally goes into 1 0 times, but we are interested in the remainder, which is 1. Then you note these values from bottom going up. Note them from bottom going up. And so from bottom going up, we're noting the remainders. From bottom going up, that's what we get. So this is the binary number. And we had the decimal number here. Now, there's one thing that I just want us to, I want to show you before we proceed, because it will be recurring. We will meet it later. It will be very important to us. Let me show you again something here. Let me convert this number 4 to binary. We convert it 4 to binary. 2 goes there twice. The remainder is 0. 2 goes here once. The remainder is 0. 2 goes here 0. The remainder is 1. So 4 is the same as you note the remainders from the bottom, 1, 0, 0. So this is the binary number. Now, there's something I wanted us to look at. 4 is 2 raised to 2. 4 is 2 raised to 2. And so you can see 2 zeros because of this power. Because of this power, you can see 2 zeros. And then 1. So 4 is the same as 1 with the 2 zeros. Okay, let me do this. 2 raised to 3. 2 raised to 3, I'm expecting it to give me 1, then 3 zeros. That's what I'm expecting it to give me. But let's just do it and see whether that is true. Because if it's true, then it's something very important that we'll be looking at. It will assist us later. 2 raised to 3. 2 raised to 3. 2 raised to 3, I've said is 1, then 3 zeros. Let's just see. 2 raised to 3 is 8. 2 go there 4 times. The remainder is 0. Then 2 goes here twice. The remainder is 0. 2 goes here once. The remainder is 0. Then 2 goes here 0. The remainder is 1. So you note from the bottom going up, it's 1, then 3 zeros. And that is what I had just written. So in other words, if I had 2 raised to 4 again, I would get 1, then 4 zeros. Now, what about, let me again show you something else. Now, look at this. Now, let me use this. Let me use this. What you realize, this is 3. It's the same as 2 raised to n minus 1. Okay. It's 2 raised to 2 minus 1. 2 raised to 2 minus 1. Well, that is 4 minus 1, which is 3. Then it gives you this. So what do you think? We've said 2 raised to 3 would be that. So what do you think 2 raised to 3 minus 1 would be? Because this is 8, 7. What do you think the binary number for decimal equivalent to 7 would be? Let's just do it. And then we can come up with a general rule. And I'm saying that these rules will then assist us going forward, because we just want to be given 2 numbers and we want to compare which one is larger. And we are writing them to binary first of all. Let's do 7. 2 goes there 3 times. The remainder is 1. 2 goes here once, and the remainder is 1. 2 goes here 0, and the remainder is 1. And therefore 7 would be 1, 1, 1. So look at this. Two raised to 2 minus 1 gave us 1, 1. But 2 raised to 2 gave us 1, 0, 0. Now we've again seen that 2 raised to 3 gave us 1 with 3 zeros. But then 2 raised to 3 minus 1 has given us 1, 1, 1. Now, you see, this is 8. and this is 7. And I want to compare which one is greater. I wanted to compare 7 and 8. I wanted to see which one is greater. But there's something I know, that if I have 2 raised to, our 8 will give us this, and then 7 is supposed to give us this. So you see, if you have binary numbers, you're able to tell which one is greater. You can see even how many bits these ones are. Bits, by bits we mean 0 and 1. How many bits this one has? This one has 1, 2, 3, 4 bits. And this one has only 3 bits. This one has only 3 bits. Now, when we came to 2 raised to 2 minus 1, it had 2 bits, 1, 2. And the 2 raised to 2 had 3 bits, 1, 2, 3 bits. So you can see the bits will now be telling us this one is greater, this one is smaller. When you count how many bits it has. When you count how many bits it has. But I think we shall look at that again. I was just trying to look at it at this point, but it will again come. We shall again look at it while looking at the bits. And of course, that is what will be assisting us to tell that this number is greater than this one by looking at how many bits it has. Now, at times it will have the same bits, of course. There are numbers that will have the same bits. But again, we will tell which one is greater by looking at those bits. So let's just proceed and see how that then unfolds. Now, I've said we've converted these numbers to their respective decimal binary numbers. We've converted them to their respective binary numbers, and I've said each digit in a binary number is what we call a bit. Each digit in a binary number is what we call a bit. And the bit, by bit, we just mean either 0 or 1. That's what we mean by bit. And then we have the leftmost bit, which we call the most significant bit. The most significant bit in our case, this is our most significant bit. And this is the least significant bit. The least significant bit. Okay. Now, so just using this example again, using this example, you can identify that this is the most significant bit, and this is the least significant bit. So by most significant bit, we shall use this abbreviation, and this abbreviation shall mean the least significant bit. Now, so we have seen how to convert a binary number to a decimal number. So for instance, what we've just done, using this decimal, supposing this is a binary number. Supposing this is a binary number. How do you convert to decimal? We say that this is the least significant bit. This least significant bit, let me write it properly. The least significant bit is multiplied by 2 raised to 0. Then the one that follows, B1, is multiplied by 2 raised to 1. Then the one that follows, B2, is multiplied by 2 raised to 2. Then the one that follows, B3, is multiplied by 2 raised to 3. It can be written this way, or even you can replace 2 raised to 3 as 8. And then 2 raised to 2 before. And then 2 raised to 1 will just be 2. And then 2 raised to 0 will be 1. So this is how we write. If the number was 4 bits, if this number, these are 4 bits, 1, 2, 3, 4. There are 4 bits. And so we would then write it this way. It's a decimal number. That's how you convert to a decimal number. But you've just seen how we've used in our previous example, how we showed that this 8 was greater than 7 by, first of all, converting 8 to binary and then converting 7 to binary. And we were able to tell that 8 were greater than 7. But again, we'll be looking at that. Now, so look at this. How many bits are these? 1, 2, 3, 4. And how many bits are these? 1, 2, 3, 4. So how do you tell which one is greater between 10 and 9? How do you tell which one is greater by supposing you're just given this and you're given this? Of course, you can tell which one is greater. Okay, they have all begun with 1. They have all begun with 1, but you can see as you move along, this one has a 1 here, and this one does not have. So then this one becomes greater than this. But we shall look at what happens later. How do we compare? Is that how we compare? Is that how we tell that two numbers, one number is greater than the other? Now, so I'm not going to details of how to convert decimal numbers to their equivalent binary numbers. Of course, we've looked at examples above. You can do that using a code, and the code that we'll be using is the one I've just put here. This code is able to give you, once you give it a decimal number, it will always give you, it's a binary equivalent. So let's give it its binary equivalent. Let me just share it again so that you can see that every time you give it a decimal number, it's supposed to give you a binary equivalent. Now, so I've input my numbers here. I've input my numbers here. And I want for each numbers to print the binaries, to print the binary of each of the numbers. That's what I want. So just tell it, go run. Then it will give me the binary numbers for each of those decimal numbers. So you can see, it's telling me that 16 is equivalent to 1, 0. How many zeros are those? 1, 2, 3, 4. Oh, of course, that's what we looked at that earlier, because 16 is 2 raised to 4. 16, and I had already shown that example. 16 is 2 raised to 4. So it means 4 zeros. 1, then 4 zeros. You can see 1, then 4 zeros. Okay, let me make it 8. Make it 8. Because 8, we know that is 4 raised to 2 raised to 3. So I expect 1, then 3 zeros. I expect 1, then 3 zeros. Just see if that happens. Go run. Okay, so it has told me that 8 is 1 with the 3 zeros. 1 with the 3 zeros. Okay, so this is 8. What about 7? 7, I expect 7 to be 3 ones. Let me just see. Expect 7 to be 3 ones. It's a 3-bit. 7 is a 3-bit. Yes, 3 ones. Because this one is 1, and then 3 zeros. How many bits are these? 1, 2, 3, 4 bits. But this one is 3 bits, and so on. Okay, so if you want to convert decimal numbers to binary numbers, you can always use this code. It's very, very easy to use. Just put the number you want, and it gives you its binary equivalent. So the B here, The B here means binary. The B is just for binary. Okay, so if you're interested in that conversion, that is okay. You can use that code. But our interest is just to, how do you construct arithmetic circuit for comparison? And that is that one that will verify that a given list is sorted, is well sorted. That means, in other words, the elements of that list are well arranged in ascending order. How do you write an arithmetic circuit? How do you write an equation that will do that? And so we said, because sorting requires the use of greater than or equal to, which is not part of what we do in arithmetic circuit, we have to move around it by, first of all, converting the values to binary. And then after converting to binary, now from there, we will then write an equation that does compare. One that it does compare. So that's what I want to look at here. I'm saying constructing an arithmetic circuit for binary encoding. So how do you now construct that? For 4 bits, these 4 bits, we've seen that we can write an equation this way. For the 4 bits we've seen, we can write this equation, and this equation will be converting the binary to decimal. So this is our decimal number. And this is how we convert it, how we convert the binary number to decimal. So this is the circuit. This is the circuit for, if we are given a 4-bit binary number. If you're given a 4-bit binary number, this is the circuit for writing its decimal equivalent. This is the circuit. But now, how do you see, for you to write this, you must also ensure that the bits you're given are either 0 or 1. So for the bits to be either 0 or 1, you have to add the following constraints, the following equations. You must add the following equations. That B0, the first one is B0 into B0 minus 1 is equals to 0. Doesn't mean. Okay. B0 into B0 minus 1 is equals to 0. So what this means, when is this equation satisfied? This equation is satisfied only if B0 is 0 or B0 is 1. So that is why I've said we must ensure that each bit is 0 or 1. So the only time this is satisfied is when B0 is 0 or B0 is 1. So for instance, if B0 is 0, then multiplied by whatever is inside this bracket, the answer will be 0. And if B0 is 1, then that means whatever is inside the bracket is 0, because it's 1 minus 1, that gives you 0. So you multiply by whatever is outside, the answer becomes 0. So the same thing here, this equation will be satisfied only if B is 0 or B is 1. Or B1, if B1 is 0 or B1 is 1. So that if B1 is 0, so we have 0 outside, it doesn't matter whatever is inside the bracket, the answer will be 0. And if B1 is 1, That means it's 1 minus 1 inside the bracket. So inside the bracket, the answer becomes 0. So it doesn't matter whatever is outside the bracket. So since whatever is inside the bracket is 0, multiplied by whatever is outside, the answer will still be 0. So all these equations, all these constraints will be satisfied only if B0 or B1 or B2 is 0 or 1. So these are constraints that then ensure that the number you are dealing with has bits 0 and 1. So therefore, this number is binary. So we wanted to write an equation, a circuit. So we then saying that this circuit, the circuit will be this, then you would add these other equations, that circuit. So this point here, I've already emphasized it. I've already said that the constraints given above are just meant to ensure that the values you are dealing with are valid binary numbers and that they correctly represent the V above, the decimal number above. So that if the condition is not, if those conditions are not met, then it means the binary number you're dealing with is not binary. The number you're dealing with is not binary. And therefore the circuit is not fulfilled. Now, so why is this important? This is important, we say it is important in cryptography, because in cryptography, and I'm looking at this range, in cryptography, you have the prover and the verifier. Prover and the verifier. Now, one of these claims to know X. The other one wants this one to show that indeed he knows X. Now, this guy is not going to say what X is. He's not going to say what X is, but he's just supposed to show that, of course, he knows what X is. So he'll then give us, he'll give a value of X. Give a value of X. And this other guy needs to know whether this X that has been given is correct or is in a given. Because the one that wants to know whether this one knows wants to know if the value is given lies within a given range. So if the value that is given lies within the correct range, then the prover is certain that this guy knows what X is. So the one who is giving X and hiding it is hiding X and giving it some values. He's supposed to give those values within a certain range. Outside that range, the values he's giving are not valid. They're not valid. So they should be within a given range. So then the one that is doubting whether he knows is supposed to know that the value that has been given is within the right range. So if it's within the right range, then that is proof enough that this guy knows what he's talking about. That is enough proof. But once he gives outside the range, then that is a proof that he doesn't know what X is. So that then leads us to range checking with binary encoding. So the highest value that can be represented for 4 bits, you see 4 bits, the highest value would be this for 4 bits. And this is 15. Because 14 will be less than, it will not be this. What would be 14? 14 into binary, it will go there 7, the remainder will be 0. And then it will go there 3 times, 2 will go there 3 times, the remainder will be 1. 2 will go there once, the remainder will be 1. And the 2 go here as 0, and the remainder will be 1. So 14 will be 1, 1, 1, 0. 14 will be 1, 1, 1, 0. This is 15. This is 14. What would be 13? What would be 13? 13 as a binary number. 2 go here 6 times, the remainder will be 1. 2 go here 3 times, the remainder will be 0. 2 go here once, the remainder will be 1. 2 go here 0, and the remainder will be 1. So 13 as a binary number will be 1101. So you can see as you go down there, they're reducing. As you go down, they're reducing. So the highest 4-bit, the highest 4-bit number will be 1111, which is 15 in decimal. And the least, what will be the least? The least will be 4 zeros. But that is not important. It's not important. What is important is this, the range. We are looking at the range. The number that we are being given by this guy who is verifying that he knows X should be not be more than 15. So if you convert to bits, the highest it should be is 15. So if you convert to bits, that number should be 1114 bits or less. So you can now see what we began by. We began by looking at how do we come up with greater than or equal to in arithmetic circuit. How do we come up with that relationship, greater than or equal to? And you are seeing how it's coming in. You're seeing how it's coming in because it's not, you cannot write it directly in arithmetic circuit. So you're saying, since you're looking at 4 bits, and this is just an example, looking at 4 bits, the highest 4 bits we can have will give rise to 15, which is a decimal number. So it then means if the number we are looking for is greater than 15, then the constraints above, the ones we've just looked at, those constraints above will not be satisfied. If the number is greater than 15, then those constraints will not be satisfied. Because what was the constraint? Let's just go back and see what the constraint was for 4 bits. The first constraint for 4 bits, was this. So this is a 4-bit, and this is a constraint. It's equals to V. So in our case, V is 15. So if it happens that this guy is giving us a number that is 17, for instance, then this constraint will not be satisfied. This constraint will not be satisfied because 17 will now not even be 4 bits, it will be greater than 4 bits. Even 16 is not 4 bits. 16 is greater than 4 bits. What is 16? What is 16? How many bits is 16? 16 is 2 raised to 4. 16 is 2 raised to 4. So if it's 16 is 2 raised to 4, it means it's 1 with 4 zeros. So 1, 2, 3, 4, 5. This is a 5-bit. 16 is a 5-bit. Yeah, 16 is 1 with 4 zeros. And the 4 zeros, I just found it here. So 2 goes here 8, the remainder is 0. 2 goes here 4, the remainder is 0. 2 goes here 2, the remainder is 0. 2 goes here 1, the remainder is 0. And 2 goes here 0, the remainder is 1. So writing from the bottom is 1, 0, 0, 0, 0. 1 with the 4 zeros. So 1 for 16 now is not a 4-bit. It's now a 5-bit. So that means the first constraint would not be satisfied. This guy claimed to know what X was. And if he's giving us an X that is beyond 4 bits, then it's telling us that, of course, he doesn't know what X is. That once he gives us any value within the 4-bit, we, of course, he's telling us he knows what X is. And we also know where X is supposed to lie. That range We know where X is supposed to lie. We don't know, we also may not be knowing what X is, but we know the range. So once we know where the range is, if it lies and gives us outside that range, we know that it has lied. So that is what this point is saying. The point is saying, thus, if V is greater than 15, the constraint cannot be satisfied, ensuring that it cannot be satisfied. So that means at every time, V is supposed to be less than 16. In other words, it's supposed to be 15 greater than, less than, or equal to 15. So this type of constraint in zero knowledge proof is what we call the range check. In a zero knowledge proof, we have what we call the range check, and it's very important that we get to know what it is even before we begin zero knowledge proof. What do we mean by range check? So that is, you, as the prover, you also know that this guy is supposed to give me a value within this range. So if it goes beyond this range, he's lying. Now, so I've just looked at an example of 4 bits, but it doesn't mean that every time it must be 4 bits. It can be 5 bits, it can be 7 bits, it can be n bits. So what about if it's n bits? The formula is the same thing. The formula is the same thing. 2n minus 1 by bn minus 1. So just the same formula as the one we used above. And then plus these other constraints. So those are the arithmetic circuit for encoding the binary circuit. Now, so then I'm asking myself, why is this useful in zero knowledge proof? Why is what we've discussed useful in zero knowledge proof? Even before we proceed looking at it in deeper details. I've said in zero knowledge proofs or ZKPs, we often need to, 1, prove a value is within a certain range without revealing that value. That is one way. And you can see we must know range check for us to prove that this value is within this range. We don't need to know what the value is. We don't need to know what it is, but we need to know that it's in the right range. Then the other way, the other part that is it will be used in zero knowledge proof is to enforce valid representation of numbers, e.g. ensuring that a value is a valid binary representation. The value we've been given, we have to ensure that it's valid binary representation of V. We've been given a binary number, so is it the correct binary number for the decimal number that we were given? So that is again where we need to be sure. Then this circuit, the above circuit, proves that V is a valid 4-bit integer. V is a valid 4-bit integer, i.e. it lies between 0 and 15. So once it goes beyond 15, then it means the circuit will not be valid. So it ensures that the prover cannot cheat by providing an invalid V. So the one that is trying to prove that he knows, he cannot give us an invalid V. Now, that is one way where it's used in zero knowledge proofs, but it's also used in confidential transactions. And in confidential transactions, what this knowledge that we're just learning, where it's used in proving that an amount is within a valid range without revealing the amount. You just want to know the amount that we are receiving. Is it within the range? And so on. What about in digital signatures, ensuring that values are correctly formatted? And also we can use it in identity verification to check whether the constraints or checking the constraints on the secret values. So these are some of the ways where it can, maybe we if we begin zero knowledge proof, we shall maybe look at each of this and see how this knowledge is useful in each of these. Now, so just if I briefly want to look at constraints, bit constraints, and storage. And this, we've already talked about it. Only that we never looked at storage. Storage is how many bits are you storing, for instance. Now look at this. N bits, 2 bits. What's the maximum value of 2 bits we can have? Maximum value of 2 bits we can have is this. 1, 1. The maximum value of 3 bits is this. Now, what is this? What is this? Let me begin from here. Now, we had this. We looked at this. We looked at 2 raised to 3. 2 raised to 3, this is 8. And 8 is 1. These are 4 bits. These are 4 bits. 1 with the 3 zeros. But then, when you write 2 raised to 3, then minus 1, this is 7. And 7, as a decimal, it will be 3 ones. It will be 3 ones. So this is the largest. This is the largest 3 bit. 3 ones. This is 7. Now, what about this? This is 1, 2. 1, 2. So if you had 2 raised to 2, 2 raised to 2 by 3 bits. 1 with the 2 zeros. 1, 2. This is 4. 4 is 2 raised to 2. 1 with the 2 zeros. So this is the least. This is the least 3 bit. This is the least 4 bit. This is the least. Because 4 bits begin from here, you can see this is 8. This is 8. Let's check what 9 is. Let's check what 9 is. Because it's the next 4 bit. So this will be 2 goes here twice. No, 4 times. The remainder is 1. 2 goes there twice. The remainder is 0. 2 goes there once. The remainder is 0. And then 2 goes. You can see 9, writing it from the bottom, would be 1 with the 2 zeros, then 1. That's a 4 bit. This is a 4 bit. But I said, this is the list. Now, the beginning point of the 4 bits, this is 1, 0, 0, 1. Then, from there, I would have 9, which is 1, 0, 0, 1. What about 10? Let me just look at 10. 2 go there 5, and the remainder is 0. 2 go here 2, the remainder is 1. 2 go here 1, the remainder is 0. Go here 0, the remainder is 1. So 10 is 1, 0, 1, 0. But how many bits are they? 1, 2, 3, 4. How many bits? 1, 2, 3, 4. Even this is 4 bits. So in terms of storage, they require the same storage. 4 bits will require the same storage. 3 bits will require the same storage, all of them. Now, what is the highest 4 bit? The highest 4 bit is the least 4 bit. So the highest 4 bits is supposed to be 1, 1, 1, 1. 4 ones. And this is 16. This is the highest 4 bits. Now from 17, we go to 5 bits. Go to 5 bits and so on. And 17, that will be now the, no, is it 17? Okay, no. This is not 16. 16 is supposed to be 2 raised to 4, which is 1 with the 4 zeros. So this is 15. This is 15, 1, 1, 1, 4 zeros, 4 ones. Because 16 will be 1 with the 4 zeros. So 16 is a 5 bit, but 15 is a 4 bit. It's a maximum, the maximum 4 bits. In terms of storage, this will require a maximum. Now, so all the 4 bits will have the same storage, and then 5 bits will be the same storage. So the thing I want us just to look at, is the difference between 2 raised to n and then 2 raised to n minus 1. And you can see, as we've seen, in this case, this would be n plus 1 bits, and this would be n bits. So this will require n bits, and this will require n plus 1 bits. And let me just show an example here. 2 raised to 4. 4 plus 1 bits, 1, 2, 3, 4, 5. 4 plus 1, 1, 2, 3, 4, 5 bits. 2 raised to 2, which is 4, will be 2 plus 1 bits, which is 3. 2 plus 1 is 3. So 1, 2, 3, 1, 2, 3. And now, when you talk of 2 raised to 2 minus 1, so that is, like in this case, is 3. This is 3. And now, how do you get the bits? How do you get the bits? That will be just 2. That will be 2, the 2 here. The 2 here. So you can see 2 bits. And so on. That is just in terms of storage, that, for instance, 3 and 4 require different storage. And then 16 and 15 require this different storage again, and so on. They will not require the same storage. Now, how is the knowledge of storage important for us? And in terms of comparison, what we want is to compare the 2 numbers. One is greater than the other one, or equal to the other one. So that is what we are doing. So why is this issue of storage coming in? How is it important here? In other words, how are bits important? Knowing that this one is 3-bit, knowing that this is 4-bit, how is it important? And that is what I've discussed here. That's what I've discussed here. I've said the number 2 raised to n would be n minus 1 bits. So in fact, this number in binary would begin with 1, then followed by n zeros. Begin with 1, followed by n zeros, and that will be the binary equivalent of this number. For instance, 2 raised to 4, you begin with 1, then 4 zeros. But now, how many bits are these? 4 plus 1 bits. 4 plus 1, so that gives you 5 bits. What about the number 2n minus 1? 2n minus 1, for instance, 3, 7, and so on. So this number would be how many bits? How many bits will this number be? But before even that, this is n. This is n. So this number, how is it in binary? In binary, this number is 1, 1, n times. 1 n times. For instance, when we talk of this, which is 15, when we talk of this, which is 15, it's just 4 ones. 1, 2, 3, 4. It's 4 ones. So this is the binary equivalent of 15. And since 15 is written by this, we can easily tell how we can easily write it, its binary equivalent. And we can easily tell how many bits it is. Since it is n minus 1, we just say it's n bits, which is 4 bits. Now, so therefore, to store V, which we had written above, if you wanted to store it in less than 2 bits, of course, we are talking about the range. So we want to store it and see whether it will fit in the range we are storing it. That is why this knowledge is important. So for us to store V in less than 2n bits, we must ensure that it fits within n bits. For us to store it here, how many bits are these? These are n plus 1. N plus 1 bits. But I want to store it in a value that is a space that is less than this. To store a number V that is less than this, So this is n plus 1 bits, but we want it to be n bits. Want it to be n bits or less. That's what we mean. Wanted to store it here. Wanted this number to be n bits or less, not n plus 1 bits. So we must ensure that it fits in n bits, meaning that the maximum possible value it can be is 2n minus 1. So this is what we shall then, this understanding is then what we'll be using in zero knowledge proof. So let me just show an example. Let's show an example. I want a number that is less than 16. A number that is less than 16. 16, we've already said, this is 4 plus 1 bits. So this is 5 bits. This is 5 bits. But I want a number that is less than this. So the number that is less than this, the maximum it can be, the maximum this number that is less than this, the maximum it can be is 2 raised to 4 minus 1, which is 15. And this number is 4 bits. This number is 4 bits. So the maximum it can be is this. So that means the prover is supposed to tell me that he knows X. And he gives me his value of X, not the exact X, but a value, just another value. That maybe that value will meet some conditions, and then I'll verify that it's correct. But now, once I get this value, what I only need to know, first of all, that is this value in the right range? Is it in the right range? Does it have the correct bits that it's supposed to have? So if I know that maybe the value that is X is supposed to be less than 16. So I'm expecting this guy to give me, if he's giving me a value that he claims to be X, that value must be less than this. So that means the maximum that value can be is 4 bits. Maximum that value can be is 4 bits. Once it goes beyond that, that is one reason as to why I should now doubt whether he knows what he claims to know. So that is, we'll be using that in zero knowledge proof, just for that particular reason. Now, so supposing it gives us the V, supposing it gives us the V that he claims to know, and we compute, we take 2 raised to n minus V. He has given us that V. And then we compute this. The result is supposed to be an n bit. Now, if it fails to be an n bit, then again, we have a reason to doubt this guy. He has given us v, we just take 2 raised to n, then minus v, and then see whether the result is an n bit. Now, for example, this is an example. Supposing n is 4, and he has given us v to be 7. He claims to know v, he has given us v to be 7. What we would do, we would take 2 raised to 4, then minus 7. We want to see what we get. Two raised to 4 minus 7 is 16 minus 7, which is 9. 9 is this. How many bits? So just count 1, 2, 3, 4, 4 bits. Then we have given a benefit of doubt because the value has given us is a 4 bit. So we can give this guy benefit of doubt. But supposing the value we would have gotten will not be a 4 bit, then we would say that the V as given to us is not correct. So this property, as I've noted here, helps us to enforce the range constraints in zero knowledge proofs by ensuring that the secret values remain within expected limits without revealing those what secret values are. We don't need to reveal what those secret values are, but we just need to show that they are within a given range. They are within a given range. Now, so I think I should stop there, but now when you later on, I'll share these notes, then you'll be able to look at how to compute greater than or equal to in binary. How do you compute greater than or equal to in binary? So I've added these notes. But now for you to, just to give you a hint of what we'll be doing here is, I'm talking about for instance, if we are talking about 3 bits, we're talking about 3 bits. I identify the largest 3 bits and the least 3 bits. And then we have the mid. So this is where 1 begins. The rest we had 0, 0, 0, 0, 0. This one began with 0, this one began with 0, this one began with 0, that began with 0. So you can see all these are begun with zeros. But then after that, we have this that begins with 1s. But then we have, finally, we have 1, 1, 1. So this is the highest 3 bit we can have. This is the center. So from here, we can now compare. We can now begin comparing. You see, we are not introducing greater than or equal to directly, but we are converting those numbers in binary. And as you convert to binary, you can see which one is greater and so on. So the midpoint is here. So from the midpoint, we can see these ones, which one is a greater here by just looking at them. And then which one is a greater here by just looking at them. By looking at the most significant bit. But then I'll share these notes, you look at them, and then see how do we come up with greater than or equal to in binary. Okay, so I want us to stop there because of time. Then I'll share these notes. We look at them later. Then after you've looked at them, I think we can then look at the last subtopic before we begin looking at zero knowledge proofs. Because there are so many things, building blocks that we require to have before we look at zero knowledge proofs. What kind of knowledge are we supposed to, first of all, have. So that when you go to zero knowledge proofs, we can easily write and verify computations in zero knowledge proofs. Okay, thank you.